Okay, so that was precipitation reactions. Another group is neutralization reactions, or acid-base reactions. So we need to talk a little bit about acids and bases. We've learned a little bit about acids. Acids form hydrogen ions in solution. We can recognize them because their formulas start with H. If it doesn't start with H, it's not an acid. If it starts with H, it is an acid. Practically, acids have a sour taste, and you've actually, if you had orange juice this morning, you drank some acid. Oh, yeah, your stomach's also full of acid, and you'd die if it wasn't. So, we don't go around eating chemicals, but in the lab, but we do eat chemicals in the kitchen, because otherwise we'd have nothing to eat. So acids have a sour taste. They can dissolve some metals, but not all metals. Bases tend to form hydroxide ions. There are other definitions of bases, but this is what we're going to use for right now. Bases tend to form hydroxide ions in solution. And the bases we're going to use are for the most part, just metal hydroxides, things like sodium hydroxide, barium hydroxide, stuff like that. Bases taste bitter. They do not taste good, and they feel slippery. I warned you in one of our labs that if you've spilled sodium hydroxide on your hands, it's going to feel slippery because it's making soap with the oils on your hands. And if you leave it on there, eventually it'll start to dissolve your skin. So if you feel slippery, then you go wash it off. Here are some common acids and bases. We notice all the acid names have the word acid in them. Hydrochloric, hydrobromic acid, nitric acid, etc. Here's acetic acid. All the formulas start with H. Here are some common bases. Sodium hydroxide, lithium hydroxide, they all end with hydroxide. And when we look at the formulas, it's a metal and hydroxide. So an acid-base neutralization reaction is a reaction between an acid and a base. So in that way, it's similar to the precipitation reactions because we have two solutions of substances that we're mixing together. But now, instead of forming a precipitate, the common product is water. So here's an example, hydrochloric acid reacting with sodium hydroxide. We can think of this in the same way of swapping partners. I might be getting ahead of myself, but I really don't care right now. So if we approached predicting these products like we did with the precipitation reactions and wrote these as their individual ions and swapped the partners, over here we've got the sodium ion and the chloride ion. And here we've got hydrogen ion and hydroxide ion. And you might want to put that together as HOH, but then hopefully that looks kind of funny. Right? What? Oh, yeah, H2O. Just put the two hydrogens together. Okay, so these are doing that same thing. They're swapping partners, but now instead of making a precipitate, a solid ionic compound, we're making a molecular compound, water. This other compound is called salt. Okay, so NaCl here is exactly the same as the salt in your kitchen, table salt, but chemists call any ionic compound a salt. Okay, so it'll form water and a salt, and that always makes me think of the word assault, and here is an assault rifle. This is a rifle made out of salt. There's your bad joke for the day. Okay, so the pattern here is we have an acid plus a base reacting to form water and salt. This is the ionic compound. Usually those are going to be soluble ionic compounds. When we write the net ionic equation for these acid-base reactions, many times it will be the same. The hydrogen ion from the acid reacting with the hydroxide ion from the water to form, from the base to form water, because the salt ends up being soluble. So let's do an example. Here they're asking us for a molecular equation and a net ionic equation for the reaction that occurs between aqueous H2SO4 and aqueous KOH. So they're saving us the whole figuring out what those formulas are. H2SO4 aqueous plus, leave space for a coefficient, KOH aqueous. We have to predict the products. So ideally, you would recognize that this is an acid-base reaction. This is an acid, it starts with H, that's a base, it's metal with hydroxide. If you don't recognize that, you can still do this. If you can do the precipitation reaction, let's write the individual ions and swap partners and combine them together, and that will help us identify the products. So sulfuric acid, we've got hydrogen ions and sulfate ions. There are 2 hydrogen ions, but this isn't an equation I'm writing here. I just want to know what the ions are. I don't really care how many there are. We'll take care of that later when we balance it. And then over here, I've got K plus and OH minus. So I'm going to swap partners. And hopefully at this point, you might be beginning to recognize, oh, look, this is going to make water. This might be an acid-base reaction. So we'll put the hydrogen and the hydroxide together, and we'll put the potassium and the sulfate together. If you hadn't clued into this being an acid-base reaction, you could definitely go to the solubility rules and see that this is a soluble ionic compound. So when I put those 2 ions together, I get K2SO4, and that's aqueous. And when I put these 2 together, I get H2O. If you do this, oops, not aqueous, because really, how can water be dissolved in water? What is water at room temperature? It's a liquid. So we write that as a liquid. It's not dissolved in itself. I almost did that. If you wrote HOH, say, on something I was grading by hand, like a worksheet, I wouldn't count it wrong, but I would snicker as I corrected it. So it's like my second son, when he was about 2, we were at a restaurant, and he kept pointing over towards the receptionist station and the hostess station, saying something about a dollar biller. We're like, what the heck? And we finally figured out he was talking about the cash register. It was a dollar biller. Oh, well, okay. He didn't know what the name was, so he made one up. So HOH, I will understand what you mean, but you're going to sound like a 2-year-old. Okay, so there's my molecular equation. Is it balanced? No. So here we have the hydroxide. It really is staying intact, but it's hard to see it over here. So we probably don't want to think about hydroxide by itself. There's oxygens here and oxygens there, and then there's hydrogens all over the place. I'm going to start with potassium because that looks easier. So I've got 1 potassium here, and I've got 2 over there. I know how to fix that. I'll put a 2 in front of the KOH. You can treat the sulfate as an intact molecule or intact ion if you want, but you can also treat it as individual atoms. So I'm going to do that just for change. So I've got 1 sulfur atom here and 1 sulfur atom there, so that's okay. Hydrogens, I've got 2 hydrogens here and 2 hydrogens there, but over here I only have 2 hydrogens, so I need 4. So I better put a 2 in front of the water. Now I've got 4 hydrogens on each side, and now I need to count oxygens. So I've got 4 oxygens here, and 2 in this, and here I've got 2 and 4, 6 and 6 on each side. Ta-da! There's my molecular equation. I need the net ionic equation also. Well, I kind of have a skeleton of the complete ionic equation down here, don't I? Would I separate H2SO4 aqueous into ions? Yes. It has AQ. If it has AQ, you separate it. If it doesn't, you don't. So this has AQ, I'm going to separate that. Should I separate water into ions? No. So for my net ionic equation, I don't want to separate the water. So I'm not going to use that. And then this one's also aqueous, so I want to separate that into ions. So for my complete ionic equation, which I don't really have to make beautiful because I just need to get to the net ionic, I've got this guy instead of the ions. And then I've got potassium ions and sulfate ions on this side, and on this side I've got potassium ions, hydroxide ions, sulfate ions, and hydrogen ions. What are the two spectator ions? Potassium and sulfate, right? Potassium isn't getting changed, it's just hanging around, and sulfate isn't being changed, it's just hanging around. So then let's write down what's left. I've got hydrogen ion, that's aqueous, and I've got hydroxide ion, and that's aqueous, and I've got water, that's a liquid, and then I need to make sure that's balanced. Is it balanced? Yeah. So there's my net ionic equation. Just like that previous example, we end up with the same net ionic equation. Most acid-base reactions have this same net ionic equation. Any questions? Yes?
When you're saying that potassium is being changed, that's because it's not binding with anything, right?
Right. The potassium was in solution as a potassium ion before the reaction, and it's in solution as a potassium ion after the reaction. Nothing happened to it. But hydroxide and hydrogen got tangled up into a water molecule. Any other questions? Some reactions form gas as a product. So we call these gas evolution reactions. You mix some stuff together and a gas forms. Often you'll see this as bubbling or fizzing. Some of them form a gas directly, like if you mix sulfuric acid and lithium sulfide. When you switch partners here, you get lithium with sulfate and you get hydrogen with sulfur. And H2S actually forms a gas. It's hydrogen sulfide, and it stinks like rotten eggs. And that'll bubble out of the solution. Other reactions give us an intermediate product that isn't stable and decomposes. So if we mix hydrochloric acid with sodium hydrogen carbonate, it's baking soda, and we swap partners there, we end up with carbonic acid and salt. Well, carbonic acid is not stable in water. It decomposes. It decomposes into a water molecule and a CO2 molecule. Carbonic acid is what they use to carbonate soda. The bubbles are the carbon dioxide coming out of solution. So these are called gas evolution reactions because a gas is evolved during the reaction. So there are 4 different types of gas evolution reactions that you should learn. And here's the table from your textbook showing them. So the sulfides. The way to recognize this one is if it forms H2S as one of the products, you just need to remember H2S is a gas. It doesn't dissolve in water. It's a gas. Carbonates and bicarbonates, you're going to get this intermediate product. So if you swap partners and you get H2CO3, you should remember, okay, that's going to fall apart. This is a gas evolution reaction. Sulfites and bisulfites, you're going to end up with this H2SO3, sulfurous acid, as an intermediate. Also not stable, will decompose. Or if you have ammonium with hydroxide, you get an ammonium hydroxide, that's also not stable. That decomposes into ammonia and water. And ammonia smells really bad also. So, how can you remember what these things are doing? It's actually a little easier than you might think. Is there, no? Okay. So let me show you how I remember this. The H2S, you just memorize that one. The H2CO3. We had H2CO3, we have H2SO3, not 4, and we have NH4OH. So you need to remember that those are going to be unstable and decompose. How they do that is easier. They all lose a water molecule. So H2CO3, they're going to decompose? Yeah, that's the word. Decompose into water and a gas. So they're going to make a water molecule, and you can figure out the formula for the gas by just taking away, well, there's 2 hydrogens, those went into the water. 1 of the oxygens went into the water. What do I have left? CO2. So plus CO2, that's a gas. The same thing happens with these other 2. So sulfurous acid is going to form a water molecule. And if I take the 2 H's and 1 of the O's off of that, I get SO2, and that's a gas. Also doesn't smell very good. Very few things with sulfur in them smell good. And then this one, oops, that's not what I meant to do. I wanted to go back to red. This one looks a lot different than those first 2, but the same thing's going to happen. I need to take out a water molecule, and to find the formula, I'm going to go in there and cross those things off and see what's left. Well, so I need to get rid of the oxygen and 2 hydrogens. There's 1 hydrogen, and this is going to bump this down to a 3. And so the other substance is ammonia, and that's a gas. Okay? This is one of those topics that if you're just trying to get through this class, you could skip this one and you can still pass. But if you're wanting an A, or you're going on to Chem 1A, or you want to be a science major, then you should work on learning this stuff. Okay? Any questions? So when we're writing equations for gas evolution reactions, you're going to write the skeletal equation with the reactants and products, just like we did for the precipitation reaction. So you swap partners and you write down what you get. You need to look at the products. If you've got H2CO3, H2SO3, or NH4OH, then you need to do that decomposition. It's going to lose a water molecule, and then you're going to have as a gas whatever's left and balance the equation. If you form H2S as a product, you just have to put gas as its state symbol. Let's do an example. Molecular equation requested for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So we're going to approach this like we approached the precipitation reactions. Hydrobromic acid, is that a binary acid or an oxyacid? It's a binary acid. The prefix hydro tells me it's just hydrogen and bromine. So I've got hydrogen ion and I've got bromide ion, and when I put those 2 together I get HBr. That's my hydrobromic acid, and that's aqueous. Potassium sulfite, potassium ion, and sulfite ion. Sulfate is SO4, sulfite is SO3. They both have a 3- charge. So you get K3SO3, and that's aqueous. Now I'm going to just swap partners here. So I'm going to get K plus and Br minus. And I'm going to get H plus and SO3, 3 minus. And I put those together, I get KBr, that's aqueous. And this would give me H3. Okay, shoot me. What am I doing wrong here? I know, I just figured it out. What's the charge on sulfate? It's 2 minus. So this is, at least I was being consistent. It should be K2SO3. I'm like, that's not looking correct. H2SO3, that's better. When you see H2SO3, you should go, oh, wait a minute, that looks kind of familiar. That might be one of those gas ones. And yes, it is. So this is going to decompose into water and SO2 gas. So when I write the molecular equation, I'm going to have HBr aqueous plus potassium sulfite and then I'm going to have potassium bromide, but instead of writing sulfurous acid, I'm going to write H2O liquid and SO2 gas. Now I've got all the players I need to balance. Hydrogen, there's 1 here, there's 2 there. Okay, we can fix that. Put 2 in front of HBr. Here I've got 2 BRs, and over here I only have 1. So let's put a 2 there. Here I've got 2 potassiums, and oh cool, I got 2 potassiums. Got 1 sulfur and 1 sulfur. I have 3 oxygens. I have 1 oxygen there and 2 oxygens there. Ta-da! 3 oxygens. So there's the molecular equation. Any questions?